back to my limit series. Today, we are going to be doing a proof. We will be looking at the limit as x approaches a constant, which we will call x naught. And our function that we are evaluating the limit at is also a constant. So this reads, the limit as x approaches x naught of L, where L represents some constant in the real numbers. Now for some of you this might seem obvious, and some of you might seem confused. We have a function here, but it doesn't really appear to be dependent on our x value. So there's not really something we can plug in per se. To give an example of what this is and why it is what it is, we can draw a graph. So if we have an x and a y-axis, and let's suppose in this example that L represents a positive number, although it doesn't have to. So this value right here is L. Then our function is going to look like a horizontal line. So we can draw it as follows. Therefore, we can choose a value to be our x naught. And we see that when we look at values of x that are close to our x naught, that it appears that the function is approaching the same value that the function always is. So in that sense, right, we can see that the limit as x approaches x naught of L, of that constant, is equal to the constant itself. Now we will prove why this is true. In order to prove that this equation is true, we want to use the definition of this limit to understand what's being said here. So this means that for all epsilon greater than 0, right? Epsilon is arbitrary. There exists a delta greater than 0 such that for all x where 0 is less than the distance between x and x naught, which is also less than delta, this means that the distance between our function, right, that we're taking the limit of, which in this case is L, and what the limit is, which is L, is less than epsilon. So what's happening here? In this case, we're trying to show that the distance between our function and our limit is less than epsilon, but our function is always equal to the limit, right? L minus L is always 0. So this is saying that 0 is less than epsilon. And how do we know that this is true? Well, we've defined epsilon to be greater than 0. And the reason why that is comes down to the definition of this type of limit. And if you're confused about why this limit definition is the way it is, I'd recommend re-watching my previous video, which goes over the definition, and that link will be in the description. But in order to prove this, right, we need to show there exists a delta, which just means that if we can find one example of a delta, then we'll show that it works. So generally, it's good practice to find your delta in terms of epsilon. So no matter how small epsilon is, we're always finding a delta that kind of combats that. So in this case, we'll say this. We will suppose that our delta is equal to epsilon. So suppose delta equals epsilon. Then we can say that the distance between our x and our x naught, right? X and the value that x is approaching being less than delta implies that 0 is less than epsilon by definition. So there we have it. This is our proof that the limit as x approaches a constant of a constant is equal to the function, right, which is a constant itself. The limit as x approaches x naught of L is equal to L. This proof also serves as a proof that our function L is continuous, but perhaps that's left best as an exercise to the viewer. Thank you very much for watching.